Now we welcome Mubashar Sarfraz. He will be speaking on energy efficiency maximization for CR-NOMA based smart grid communication networks. Mubashir Sarfaraz, I request you to share the screen and start the presentation.
Hi everyone. Am I audible?
Yes, you are audible. Please proceed.
I will discuss the energy efficiency maximization for cognitive radio NOMA based smart grid communication networks. I'm currently working in this research group. The contents of my presentations will be as follows. The increasing demand for smart grid has led to many challenges, and researchers proposed different solutions by introducing the concept of renewable energy resources and by improving the traditional electrical grids that ensure reliability, sustainability, and efficiency. The transformation of traditional grids into a smart grid is done by introducing these set of smart devices that monitors and that actually sends the data and transmit it to the control center in order to take further necessary actions. Smart grid layered architecture consists of 5 different layers, and the focus of our research is basically on communication layer. That is the third layer. Smart grid predicts future actions, future electricity demands, and that helps to increase energy efficiency of the overall system. It also reduces the electricity cost by allowing bidirectional communication flow. This is the proposed communication infrastructure for cognitive radio-based smart grid communication networks. It consists of 3 different types of networks, namely as home area network, neighborhood area network, that is NAN, and wide area network. Home area networks where the end users are there and smart meters are installed that sense and transmits the data to the NAN, that is a neighborhood area network, where data collector collects the information and relays to the control center. After studying the existing research, we have found the gap that no one has integrated the cognitive radio NOMA for smart grid communication networks to improve the energy efficiency. So we propose cognitive radio NOMA for smart grid in order to maximize the energy efficiency. Our focus was to integrate the cognitive radio NOMA and smart grid communication architecture, smart grid communication in smart grid communication networks to improve the energy efficiency of the network and to meet the communication requirements. Because if we see, there are 3 different types of networks: HAN, NAN, and WAN, and the communication requirements and the communication range is also different. So it was already proposed in the literature to meet the communication requirement of the smart grid network. Cognitive radio was proposed. So in order to optimize the energy efficiency, we actually formulated a joint user pairing and power allocation problem by using NOMA, and then this problem is subdivided into 2 sub-problems, that is the user pairing and power allocation. First, we solve the user pairing problem by using the zebra optimization algorithm, and then following the suboptimal user pairing, we allocate the power to set of users. This is the proposed system model where smart meters are installed at each home, and these smart meters are responsible for collecting the demand response and the metering information, and then this metering information and the demand response information is relayed to the data center. Then data center takes the further necessary actions. There are for the simulations we assume that there are n number of smart meters deployed in the network, and there are k number of channels. The number of channels are less than compared to the number of users. This is why we use NOMA, because NOMA allows to share the single resource block among multiple users. And then we for this particular case we only assume two users for a single resource block, and we perform user pairing, and for in each single pair there are maximum two number of users. This can be increased. The transmitted signal at the NOMA user is in equation 1, and the received signal by the data collector is calculated in equation 2. Similarly, if we follow the OMA is orthogonal multiple access, where only a single resource block is assigned to a single user. So OMA is set as a benchmark, and it can be calculated by using equation 3. In NOMA, we allocate single resource block to multiple users, and for this scenario we consider two users, and then we pair together these among those users. One is the strong user and the second one is the comparatively weak users. This is basically the requirement for NOMA. And the data rate, the transmission rate for the weak user is calculated by using equation 4. And similarly, for strong users, we calculated the data rate for strong users by using equation 5. Afterwards, we formulated an energy efficiency problem, and it is given in equation 6, and it can be seen that the energy efficiency is actually the sum of both strong and the sum rate of both strong and weak user divided by the power consumed by those users. Next, we formulated the optimization problem, where our goal is to optimize the energy efficiency, and by using these three gamma, U, and P decision variables, where gamma is the number of available channel and the channel availability. And the channel availability is not same for all the users. The geolocation of the channels will be the location of the channels will be different for different set of users, and use the user pairing matrix, and similarly P is the power allocation vector. And subject to C1 to C5, where C1 is the rate requirement for NOMA, and that if we use NOMA, the minimum rate should be greater or equal to the NOMA. And C2 is for the power allocation, and C3 is actually also for the power allocation. The total power allocated should be less than the maximum power. And C4 is for user pairing. We only consider two users for a single resource block. And then importantly, C5 is the channel availability, and it is different for different users. Then we subdivided our main problem P1 into two parts, that is user pairing, which is P2, and power allocation, and that is P3. P2 is basically, we just optimize the energy efficiency by considering the channel availability and user pairing matrix. And this problem P2 is named as ZOOP, that is zebra optimization based user pairing. Then we compare the performance of the proposed ZOOP with the four benchmark schemes, and it can be seen here beta is actually the power allocation factor, how much power is assigned to the weak user, and how much power should we assign to the strong user. So if we increase beta from 0 to 1, it means that we are assigning higher power to the strong user, and it will increase the energy efficiency. But it can be seen that the proposed Zoop gives the better result as compared to the other four benchmark pairing schemes, where UPWO is user pairing without optimization, and the adjacent pairing is if two close users are paired together, and random pairing we just randomly select two users and paired together. And OMA is orthogonal multiple access one resource block for a single user. Similarly, we also test for we also tested the proposed Zoop by changing the SNR values, and similarly we also run to see the simulations to see the different diverse environments, because for this simulations we consider the suburban environment, but it can be urban or dense urban. And then what will be the effect of the proposed Zoop? It can be seen Zoop gives the better results compared to the other benchmark schemes. Similarly, we also vary the number of users. If we increase the end users, then what will be the effect on the proposed algorithm? And finally, the impact of channels availability. If the number of available channels increase, then what will be the effect of the proposed? And finally, the coverage radius. If we increase the distance between the data collector and the edge user, then how the proposed algorithm will be affected. So it is seen that the proposed Zebra optimization based user pairing gives better result for different types of tests. Then P2 is further, P1 is basically, P1 was subdivided into P2 and P3. First we solved P2, then by obtaining the optimal suboptimal user pairing, we assign power allocation to those users, and then it is named as Zupa, that is a Zebra optimization based user pairing and power allocation. It can be seen that the proposed Zupa is this is our proposed Zupa Zebra. This is joint optimization, the user pairing and power allocation, and this is single optimization. We just optimize the user pairing matrix, and this is without optimization, no optimization. The performance improvement of the joint optimization compared to the no optimization is significant, and it is comparatively better as compared to the single optimization. And we also check different set of parameters here. Chi is basically the environment, either it is suburban, urban or dense urban, and SMs are the number of smart meters, the end devices, and M is the number of channels, and then we check the effect for different coverage radius. And these are the set of simulation parameters that we use in this simulation. Okay, the results shows that the single optimization achieves better results compared to the four benchmark schemes, and the joint optimization gives significant improvement compared to the no optimization scheme. If we check for different coverage radius. And when channel availability is increased, there will be the higher number of channels, and this will also increase. This will also gives the gap for good channels, and we can assign those better channel, and it also helps to increase the energy efficiency. And finally, by increasing the user diversity and different path loss exponent for different environments, the proposed joint optimization gives better results. Okay, what are the research gaps? We can extend this research. We can also work on multiple users for a single resource block, but the main problem is actually how we deal with the interference from other users. But this problem can be extended to multiple user pairings. Similarly, this proposed problem only consider the optimization of the capacity. We assign higher power and we only optimize the capacity. But it can also be done by the other way, where we assign only the amount of power that achieves the minimum QoS, and we save the extra power. This also helps to improve the energy efficiency. The objective function, the proposed objective function, that is P1, can be break down by using the Dinkelbach formulation, and I am currently working on this problem, and we can apply different iterative convex methods, and this will gives better results, because for these simulations we use heuristics, and heuristics are not optimal, they are suboptimal, but we can achieve the optimal results by using the iterative convex methods. In cognitive radio, we consider the interweave mode. It means that a channel is available for a given period of time, and there will be no primary user. This can be extended to the other mode, that is underlay mode. The primary user, the licensed user, is also present, and we are assigning those channel resources to the unlicensed user by keeping the interference by setting the interference thresholds, and we can work to optimize the interference among the unlicensed users. We can also make a hybrid model, because if we go for the dense urban environments, there will be higher number of users, and the channels, the available channels will be lesser as compared to the higher number of users. We can also go for the hybrid model. Finally, cognitive radio can be applied to maintain fairness among the weak and strong users. I'm also working on this problem to maintain the rate fairness among the strong and weak users. Thank you very much. Any questions?
Thank you for your presentation. Does anyone have any questions or comments for Mubashar Sarfraz before we move forward? Thank you for your kind words and participation.
Okay, thank you everyone.